Well, thanks for the intro, and thanks for inviting me. It's fun. I'm Zach. Please, I hate talking at people, so please, like, speak up and harass me. And I guess I decided to open this with, like, the most videos possible on a single slide. I don't know if that was a good or bad idea. It's like a shock and awe or something. But yeah, hopefully I'll get to talk about most of these things. And I think hopefully from this you can also glean that I'm like kind of, my two loves are like weird space things and robots. So that's what we're gonna talk about. So first to open up and kind of set the stage a little bit. Hopefully everyone knows what this thing is. Definitely not. No, we have some space people in the room, right? So this is Curiosity, right? And this thing has been on Mars for 12 years, which is incredible if you think about it as like a feat of engineering, right? This thing's been in like one of the harshest environments imaginable, storms, crazy temperatures, dust everywhere, all that kind of stuff. And in that time, it's managed to travel 32 kilometers. Sounds pretty good until you divide those two numbers. So like 7.2 meters per day, roughly like, here to the other side of the room over there. This is not impressive. And, it's sort of a bummer. And unfortunately, it limits a lot of the science we can do on these things. And there's a whole bunch of anecdotes about this that I could share, but I think this kind of sums it up nicely. Does anyone know what this is? Who's been here? Maybe? No? Okay, so really letting me down on the space nerd stuff here. So this is the Mars yard at JPL. Maybe a couple of you have heard of this. So basically what this is a giant sandbox out back at JPL where they have a bunch of rocks and a bulldozer and some shovels, and they drive the rover around. So the rover can drive autonomously. It's pretty cool, but they're super conservative with it for obvious reasons, right? You can't fix stuff, you can't go get it out of a ditch, et cetera, and it's very expensive. So anytime it runs into anything scary looking, like a slope more than a few degrees or a big rock, it's set up to just stop and then like look around and send all the imagery back to Earth. And all the JPL engineers go out in this sandbox out back and try to recreate the environment around the rover on Earth with a backhoe and a bunch of shovels, and they kind of put the rocks in all the same places. And then they painstakingly hand design a trajectory for the rover to go around all the obstacles and test it a whole bunch and drive it with the real rover. And then when they're satisfied that that's gonna work, they uplink it to the rover and it executes it, and then it goes on its way. This is, as somewhat obviously, super painstaking, lots of human in the loop kind of stuff, and ultimately limits what they can do with the rover. Anecdotally, if you talk to the rover drivers and stuff, if the rover stops moving on a Saturday morning, it'll be stuck until Monday morning when everyone gets back in from the weekend. If it happens over a holiday, it just won't operate. So you'll end up losing days of operational time on this thing because of this kind of thing, and it's sort of constrained by humans, and we have to sleep and stuff and eat occasionally. So it's actually a major thing, right? Okay, and so where we like part one, everything is optimization. Hopefully some of you agree with that statement. We'll see. But I'm gonna now kind of walk through a whole bunch of of the problems that we encounter in these sort of domains that hopefully all you guys have seen before, and how each one of them at least can be posed as an optimization problem. And in there, I'm gonna mix it up a little bit and show you some of the stuff that we've done in each of these specific areas. Then we're gonna try to bring it all together. The first one, obviously, control is optimization. I don't think I have to tell you guys in this audience this, right? And usually we kind of set things up like this, and we have a model of our robot, maybe, or if you're an RL person, maybe you have a black box simulator, same thing, whatever. And then you have some kind of cost function thing that encodes what you want the system to do, right? And maybe some constraints that say, your actuator limits and don't hit stuff and whatever. And this is very powerful and very general, right? And I kind of, in this, I would sort of subsume all of, kind of trajectory optimization and RL and all of these under this kind of framework, right? And just to tease a few of the things we've been doing in this area, we work a lot on numerical solvers, and in the last year, we've had kind of fun papers on getting these things to be really computationally efficient so they can fit on tiny microcontrollers on stuff like this Crazy Fly, and do all kinds of fun obstacle avoidance and stuff all on board. We've also kind of tried to scale these the other direction and build new solvers that can run on modern compute hardware like GPUs, right? And actually take advantage of thousands of cores. This is an example of a full body model of the Atlas humanoid running at 2 kilohertz. Kind of pretty good if you know how this stuff goes typically. Okay, so that's control. Also, people in here, I'm sure, lots of people do state estimation. This is almost the same problem, it turns out. You got your model, maybe got some noise in there, and then you've got some kind of least squares loss or something that you minimize to figure out where you are. We've also done some work in this area specifically. On the space side, we've done a bunch of work on sort of satellite swarms and doing kind of distributed estimation. There's actually a mission we flew this year where we did range-only relative navigation between satellites in space and actually got down to 70 centimeter kind of 3D position error on this whole thing, which was pretty awesome to actually do it finally in space. Okay, and then kind of moving away from maybe some of the stuff that you've seen a lot of to maybe some stuff that's a little less familiar is you can also pose physics as optimization. Anyone know what this thing is? Yeah, so this is Hamilton's principle of least action. Sometimes people get really pedantic and tell me it's not least, it's stationary action, and I'll fight you on that if you want to take me up on that after this. So you can pose physics this way, right? And this is kind of for those who haven't seen this before, that Q of t in there is the pose of your system, the configuration of your system, right? And Q dot's obviously the velocity, and then this is the Lagrangian, right? So kinetic minus potential energy. And this is classical stuff that you probably saw in some kind of, intro grad level mechanics course. And then you probably did some weird calculus of variations-y thing one time that you forgot how to do. And you got the Euler-Lagrange equations, and if you're a roboticist, you maybe called that a manipulator equation and then kind of dealt with that from then on and never really went back to this optimization formulation. So I'm here to tell you that maybe you should think about this a little bit more, and there's maybe more to this. So in particular, if we kind of like squint at this for a second, this looks just like a trajectory optimization problem, where the kind of the pose or configuration trajectory of the system is kind of doing state-like things. And this is like your cost function, right, integrated along a trajectory. And we can go ahead and discretize this thing in time, just like we would do with a trajectory optimization problem, a motion planning problem, and we can directly minimize this numerically and get out physics. Kind of cool. Why would you, and by the way, this is not a new idea. This is from about 20 years ago from Jerry Marsden at Caltech, and a bunch of his students pioneered this kind of thing. It's called discrete mechanics. And there's a whole like kind of literature on this stuff, and the main takeaway is you get really cool conservation properties out of this. It conserves energy and momentum and all kinds of stuff automatically, and you don't have to, it does very nice things for you. We don't really care about that, to be honest. Runge-Kutta is fine for us, but there's some other kind of cool things. If I can get it to this state, and it looks like a trajectory optimization problem, I can apply all the tools I know how to use from numerical optimization to this. And in particular, if I care about impacts and that kind of stuff, which show up all the time in robotics, right? If I'm walking or grabbing onto something, that's classically really hard to deal with because it's non-smooth. And technically, you can't even really write that as an ODE. There's discontinuities and all kinds of badness, right? Well, if we take this viewpoint, we can actually just deal with those as inequality constraints. So if you imagine like a falling brick and you want to hit the ground, you can just say, brick's not allowed to go through the floor. And that's that inequality up there. And then I just kind of turn the crank on this and solve it as a constrained optimization problem. And all the things you expect happen. So the kind of Jacobian of that constraint becomes the normal vector. The Lagrange multiplier becomes the normal force. The KKT conditions end up kind of telling you all the things you expect about physics, and it's really natural and really cool. And this kind of, and it's all the numerics are nice, and there's no weird, super stiff ODEs. It's kind of cool. Similarly, friction, which is also annoying and non-smooth, can be posed as an optimization problem. Anyone seen this before? This is called the maximum dissipation principle. So it turns out if you minimize kinetic energy, it turns out the force due to Coulomb friction is the one that instantaneously sucks out the most kinetic energy from the system, subject to this cone constraint called the friction cone, which is really just a generalization of that whole like mu times normal force thing you saw in high school or whatever. So that's kind of cool too. Okay, all this physics stuff. And then another one that we see all the time in these kind of robotics applications is collision detection. So this is, if I'm like the falling brick example, well, if I have slightly more complicated geometry, just saying if you're touching or not becomes kind of a non-trivial problem, right? If I have some complicated robot with fingers and I want to go grasp over here, I have to figure out what the closest points between all my fingers are in this, non-convex object, and that's kind of tricky, it turns out. And computer graphics people and video game people have spent decades trying to make this work reliably and be fast, and that's all great. And it turns out we've also kind of looked into this recently from the perspective of differentiability. And as you can kind of imagine, if I take two convex objects, and I ask for the closest point between those, distance, 2 norm, that's a convex thing, and if the shapes are convex, you can kind of like convince yourself pretty easily that's a convex optimization problem. Unfortunately, though, that has some problems. In particular, if the 2 objects penetrate each other and they kind of overlap, that problem becomes ill-posed and sort of breaks. And that happens actually somewhat regularly in real data with noise and in another kind of context. So one of my PhD students recently came up with this thing, which is really slick. So it reformulates the problem. So rather than asking for the closest point, it asks for the minimum sort of scaling, uniform scaling of these 2 objects such that they just touch. And that's kind of slick. It turns out this is always well posed and always has a solution, and it's also differentiable. So you can get like nice gradients out of this for other downstream applications. Super cool. We call that decall. Okay, so collision detection. So now hopefully I've shown you like most of the problems I care about as a kind of motion planning control robotics person, at least can be posed, maybe not, don't have to be, but can be posed as optimization problems. So next, part 2. How do we put all these things together, right? So I showed you all of these pieces are nice, clean, little self-contained optimization problems. But ultimately, I need to wire it all together, right? I need the collision detection thing to inform the friction and contact physics stuff, which needs to talk to the control algorithm, right? So it all has to work together, and that turns out to be kind of tricky. So as a brief interlude into part 2, I want to talk a little bit about this kind of contact stuff, which has obsessed me for the better part of a decade now. So this all seems fine, right? This is our optimal control problem we saw before. But if I'm doing something like this little quadruped robot over here, where I'm making or breaking contact with the environment a whole bunch, I kind of alluded to before, that's non-smooth, right? So if you write down kind of normal F equals ma stuff for that, you end up with either really, really stiff ODEs that are a huge pain to deal with, or you end up with sort of switching constraints that are sort of integer flavored, which is also bad. So you kind of have this smoothness issue floating around, and it turns out standard numerical techniques for solving these problems kind of don't apply here, and you need to do something else. So there's kind of a couple ways people have typically dealt with it. One, which is, I would say, kind of the industry standard approach, is this so-called hybrid approach, and that is kind of doing that integer flavored thing where you enumerate all the times and locations where contact switches happen, and you have to do this with some kind of heuristic or some oracle or whatever. So if you know those times, then you can bake them into the problem formulation as given and basically get them out of the optimization problem. And then you're just optimizing over the smooth arcs between those contact switching events. And that's back to a problem we know how to solve well. So that's one approach. The downside is now you need some way to pre-specify those, what are called mode switches. So in legged robotics, maybe this isn't too hard if you're left foot, right foot, but it quickly breaks down and becomes intractable if you're doing like really complicated in-hand manipulation stuff where the contacts can be really rich. That can be super hard, right? Okay, so I have to say though, this is kind of, I alluded to, this is kind of the standard thing to do, and it's been really, really successful. So we've all seen these videos. This is kind of what these guys are doing, and every other really cool looking legged robot video for that matter. But these guys have taken this obviously really, really far. Okay, so the other thing I love about these guys though is they actually publish the blooper videos. So we're gonna look at one of these blooper videos real quick. And I wanna actually ask you to look really carefully at when these kind of bloopers happen. So this is a really good one that I slowed down. So what happened there? Why did it face plant? Foot touched the beam, right? So in the lingo that we were just kind of like kind of going for here, with modes and all this kind of stuff, what happened there was an unplanned contact switch. So another way of saying this, right? If I'm doing this pre-specification of footsteps and all this, the controller is really open loop on the contact modes. I have to pre-specify when those things are happening. I might have some outer loop heuristics that are trying to update those things online, but the actual control, optimal control solver that's doing this at a couple hundred hertz or whatever, it can't reason about anything like that. So when the foot touches the the ground or the beam there, the controller doesn't know about that. It doesn't know that the environment can exert forces at that location on the body. It has just no knowledge whatsoever, and it completely fails. So this is kind of, I would argue, a really deep issue that we don't currently have control methods that can reason about this kind of physics in a rigorous way. Okay, so there is another way. This is called contact implicit, and people have been working on this for decade plus, including people here. And historically, the issue with this, here you're trying to solve for the whole thing, right? The modes, the contact forces. And the problem with that, right, is all this non-smooth or integer-flavored badness. So typically, these have like really serious numerical problems. They either take way too long to solve, or you end up with ill conditioning because of stiff, ODEs, and it just kind of hasn't really worked out that great historically. Okay, so now we're going to try to like fix those problems, and I'm going to kind of walk you through the way that sort of like we've come up with thinking about this in my lab. And I call this composable optimization. So the gist is all these little blocks I just walked you through, we've developed techniques for solving those well, and ultimately we need to hook them together. And so now I'm going to talk through like how we approach that hooking together and essentially like jointly solving this entire coupled mess of optimization problems jointly, right? Okay, so the first key idea here is what we call a differentiable interior point method. We've seen interior point methods before, like pretty standard way to solve constrained optimization problems, right? Okay, so we're gonna like go with this sort of very simple prototypical problem where you've got cost function and a single like inequality constraint, just to kind of illustrate the idea. And the thing that's key here is that we're minimizing over x. So x is what we call the decision variable. And then there's this other variable floating around y, which we're not optimizing over, and we'll call that the problem data or problem parameter or something like this. So the idea is that the solution to this thing depends on y, but we're not optimizing over y. It's like this sort of input to the problem. Cool? Okay, so I said that out loud. Okay, so what we're gonna do now is imagine that this block here is the Coulomb friction box, just for illustrative purposes, right? So that's this block. We're gonna zoom in a little bit. So for illustrative purposes, right, this inequality is gonna be that friction cone thing that we talked about. And this x is gonna be the friction force. So we're trying to solve for the friction force. But remember, that thing also depends on the normal force, right? So I'm not optimizing over the normal force, but the friction answer depends on the magnitude of the normal force. So that normal force is gonna be our problem parameter, right, that this thing depends on. Okay, so, and you could flip this around, right, if this were the normal force is coming from the contact, the impact mechanics box, right? And if you flip this around, that impact mechanics thing depends on the Coulomb friction, and it's solving for the normal force, right? So there's kind of symmetry there. You can hook these all together, but they all depend on each other, right? Okay, so first trick is we take this thing, and this is just interior point methods 101. We're gonna take that inequality constraint and bury it inside this thing called a log barrier. So it's just a log, which blows up as the c of x as that constraint approaches 0, right? And we stick it in the objective function. So now we've basically removed the constraint and put it inside the cost. And just to kind of give you an idea of what this looks like, right? We have this little tuning parameter row out front, which we call the barrier parameter. The idea is as you crank that, this log, which is nice and smooth, kind of gradually approaches a brick wall, which is non-differentiable, right? So in the limit, it becomes non-differentiable, but for any finite row, it's differentiable and nice, and right, we've been doing this for decades now, and it works super well, and that sort of smoothing effect is what lets you actually get gradients out and solve this thing efficiently with Newton's method or whatever you like. Okay, cool. So this thing, we take this, and then we're gonna write down the optimality conditions for this guy, which are KKT conditions, if you know what that is, but I'll really just like basically setting the gradient equal to 0, right? Like freshman calculus kind of stuff. And set the gradient equal to 0 and solve that root finding problem for 0 right there. So that's what we're gonna call R. Okay, so that's, I take the gradient of this thing with respect to x, set it equal to 0. Still depends on y though, right? Okay, so the key next move is if I've got that, I can use this trick called the implicit function theorem. We've seen this before, a couple people. So the idea here is if I got that R of x and y, I Taylor expand it in both x and y, and I just kind of move stuff over to one side, and I can solve for dx dy. Okay, so now what this did for me is altogether now, this block, I can treat it as a normal function, x of y, and I have its derivative, dx dy. Internally, it's doing some crazy stuff with a numerical solver, but outside the box, it just looks like a normal function that I can query, and I can also query it for its derivative. So now, in principle, I can take this entire optimization solver and treat it as just any other differentiable function. I can do whatever I want with it. I can optimize with it. I can bury it inside a constraint function in another optimization problem. I can put it in an objective function, whatever I want. And this is kind of the magic trick that lets you do this wiring. Okay, cool so far? Feel free to bug me and interrupt if you have thoughts. Yeah. Turns out the log barrier is somewhat magical. There's a whole like really highly developed theory for these interior point methods. You can use other barrier functions. The main property they need to have is that they blow up to infinity at the constraint boundary. That's why they're called interior. They keep you inside the feasible region. You can use some other functions. These things, there's this magic, this is not gonna make any sense. You can look this up if you want. It's called a self-concordant function. And that's what you really want for a barrier to be nice. It basically means its higher order terms in its Taylor series are bounded in a nice way, such that Newton's method or gradient-based optimization methods that rely on Taylor expansions work well on it. So that's kind of why log is nice. There are other examples of barriers that have that property that you can make up or find, but like everyone uses log and it works super well. And yeah. You want to. You absolutely do. Yeah. So this is a thing. There's been a bunch of work on this, convex layers from Zico Coulter and others. Basically, the other option here is to, if you did auto-diffing, for example, on this algorithm, it's going to unroll the solver loop. And so this thing might take a dozen iterations to converge. If you unroll that with an auto-diffing toolbox, it's going to take a ton of memory and basically just not work. So what this lets you do is you can hand code the other thing to mention is that Jacobian, if you solve this with Newton's method, for instance, where you're already evaluating those derivatives. So this is free. So at convergence, the algorithm, I can give you that Jacobian for free, almost. Cool. Anybody else? All right. Moving on. Okay, so what do we do with this? So the first thing we did with this is we kind of wired these blocks together, like the impact dynamics stuff, Coulomb friction, and collision detection stuff. We made a simulator. We call this thing Dojo. It's kind of cool in that it has these kind of nice properties that I would argue no other simulator really has, in spite of lots of investment by lots of big tech companies. So first of all, it does real hard contact, as in, I don't get forces off the ground in the air, and I don't penetrate through the ground. Both of these are very common in current robotic simulators for various reasons. You also don't get, so you don't get any interpenetration where you sink into the floor, which things like Majoko do that a lot. You also don't get creep. So it turns out a bunch of these other simulators, they do various smoothing tricks, and they can't actually do Coulomb friction, which is fundamentally non-smooth. So they can't do stick slip. So if you put something on an inclined plane, it's always going to creep a little bit. It never actually gets sticking friction, which is annoying. And then I kind of alluded to before that we get really nice energy and momentum conservation properties because of that magical discrete mechanics stuff, which we don't necessarily care too much about, but it is nice. It means you're stable and you can take big time steps and that kind of stuff, and simulate really quickly. And the last one, right, as we already know, we can actually give you the gradients of all this stuff. That lets us do optimization and kind of outside of this in an outer loop. And a couple examples of that, right? So this is just showing you, this is like showing you the derivatives of an impact or a stick-slip transition as a function of that rho barrier parameter. So I can give you any smoothed version of this you want. And kind of one of the interesting things here is that I can simulate the hard impact, which is the black line. But then if you want to do optimization, that's terrible. So the idea is I give you the answer with the hard impact, but then if you ask me for the gradient, I give you one of those pink curves, and I cache them as I converge, and I can give you any one of those you want. So you kind of give me this kind of relaxation that you're willing to tolerate on the derivatives, but you can still get the real physics answer, which is kind of an interesting thing. Okay, so I get gradients. Now I'm going to tell you I lied to you a little bit about something subtle, and I just want to point this out because it's very subtle. And I stole this language from the FEA CFD people, which we started talking to them for some other stuff. So they have this notion of strong versus weak coupling, and this is like a good illustration of it. So the thing on the left is what I would call weakly coupled. What's going on here, if I have this collision detection box and this impact mechanics box, right? If I just treat these like functions and query them, which is what most simulators right now do, by the way. So if I have these boxes and they're about to collide, and I ask you for the closest point between the two boxes. If I have these two boxes, and let's say everything's perfect, right, and it's in my simulator, if I put them like this right on top of each other, what's the closest point between those two boxes? It's ill-posed, right? It can be anything on that surface. So how do I pick one? If I use a collision library, which is standard, right? There's FCL, there's things like this out there, and I give it that problem, it has to return an answer to me. So what's it going to do? Well, in general, it's going to regularize somehow, and it's probably going to give me something like the geometric center, right? The centroid of that face. perfectly reasonable in the absence of any other choice, right? So if I just run my simulator where I query that collision detection thing, get the point, and then plug it into my simulator with some force model and simulate a step, you get the thing on the left. So basically what's happening there is it's giving me the centroid, but it doesn't know anything about the mass distribution of the boxes or anything else. And so it turns out if you line these up off center even a little bit, they can't balance on top of each other. You get this weird unphysical artifact of them bouncing. In practice, all these simulators implement a bunch of hacks to try to avoid this, but it's there from the fundamentals of the formulation. So what you want to do instead is this thing on the right, which we call strongly coupled. So what that is really doing is embracing this idea that these things depend on each other, and you have to solve them jointly. And something really cool actually happens here. So this collision thing, where I have the face-on-face box thing that's ill-posed, it turns out if I take that problem and solve it jointly with the physics problem, the physics problem is using that least action thing. And you can kind of think of that as like an energy minimization kind of metric, right? It turns out that energy minimization thing from the impact dynamics regularizes the collision detection problem if you solve them jointly. And the answer you get out for the closest point is the one that minimizes the action, like basically minimizes the energy. And then it gives you the correct balancing point. And it all works out, and you get like sort of physically the right kind of simulation. So to explain in a little more detail like what this actually looks like under the hood, we have these two boxes, and we talked about writing down their first order necessary conditions, their gradients. So the first one I'm solving with respect to x, so that might be the collision detection stuff, and x is the closest point, and then y is like the pose, right? And then the second one might be our impact dynamics, where y is the pose, and x is the closest point, right? So vice versa. And I write down the first order necessary conditions for both of them, so gradient equals 0 stuff. I stack them together like this, so they're coupled, right? Those KKT conditions, those first order necessary conditions, they depend on each other. And if I stack them like this and solve that problem jointly with, say, Newton's method, then I get the right answer, basically. So they're able to inform each other as you iterate inside the solver and give you the right answer. Okay, so far so good? Do we have anything to bug me with? All right. Okay, so we can do lots of cool things with this. I mentioned we can get the smooth gradients and all that stuff. So you can do kind of vanilla trajectory optimization stuff. You can do RL, that's the middle one, where you actually use the gradients and just do actual gradient descent instead of like SGD kind of stuff, and that has obvious benefits. You can also do system ID, so we diff through this kind of collision stuff and solve for the box geometry. And you can do kind of other fun motion planning things. That thing on the bottom is using gradients to solve this like kind of simple motion planning problem with an arm. Okay, cool. We have gradients. So we care about doing control. We spend a lot of time thinking about trajectory optimization and model predictive control in my group. And so now we've got all these pieces, right? We could go solve this trajectory optimization problem. So we did that. Here's some examples. Punchline though, these took like 10 or 20 minutes to solve offline, which is obviously terrible and not going to be real time. So then you start asking the question, okay, I want to do this online. I want to do it in real time. What can we approximate from this thing to try to speed it up without losing the core kind of flavor, right? So we start approximating things. The key insight here is we want to keep this block structure and keep this overall sort of solver method where we're jointly solving all these optimization problems, but we're going to zoom inside each box and start approximating things inside the box. So specifically in that optimal control problem, instead of trying to solve it from scratch, we're going to solve a tracking problem. So that lets us locally approximate the dynamics and everything around some reference. That makes that easier. Inside the dynamics there, it turns out we can locally linearize a bunch of stuff. We're not linearizing anything about the contact dynamics, but like the sort of manipulator dynamics of the robot, right? We can linearize a bunch of those about a reference, do reference tracking. We can also linearize the sign distance functions in this guy, so we can approximate those in a way that's fast and cheap. And we can also approximate the friction cone in a way that's standard in robotics, but sounds weird maybe at first. So this is it's a round cone, right, like an ice cream cone. You can linearize this by approximating it as a pyramid with flat faces. That's another standard approximation. You take an inner approximation. Okay, cool. So we do all that stuff. And then it turns out we can do this really fast. So there's a couple examples. So this is one we call the punch bot. It's an inverted pendulum with a little arm, and it can push against these walls. And we've initialized this about that kind of balancing point with no other information. So it obviously knows, in there, the geometry is in there, so it kind of knows it can reach out and touch the walls, but there's no information about, contact modes or any of that in the problem. It's linearized inverted pendulum dynamics, blah, blah, blah. We hit this thing, and it can kind of reach out and figure out how to balance. This runs at a couple hundred hertz. It's pretty good. This one is one of my favorite. And this is one, like, I actually saw this and was like, okay, this is actually going to work now. So this is a quadruped model, a dumb quadruped model we call the point foot model. So it's a single rigid body with point mass feet. And the reference in here that we gave this is trotting at the origin, trotting in place at the origin. So that's all it has. It has this nice periodic linearization about the origin, just doing that trot thing. And then we just kick the crap out of it. It flies through the air, flails around, lands on its feet, figures out how to catch itself. It reaches out a little bit, and then it trots back to the origin. All of this is coming out of a single linearization. When I saw this, I was like super, because normally to get this kind of behavior out of standard methods, there's a bunch of push recovery heuristics, right? Thinking about where to put your foot so that it sort of can arrest your fall and cancel out your momentum, all this kind of stuff. This just comes right out of this. So I don't know, I thought this was really impressive and cool. Maybe it's not that impressive in light of things you've probably already seen, right? Okay, so we've done this on hardware. These are not amazing either, but still kind of cool that this actually runs at real-time rates, and it's totally, there's no contact information pre-planned in here. And we started like messing around with, if you can do this and you can reason about contacts all over the body, most of the methods out there right now assume point contacts with the feet. Here we've got all the body geometry though, so you can like do weird things with the rest of the body, which is kind of interesting. This is early stuff. We've got better stuff now that is not quite out yet, so stay tuned. Doing some fun things with this. Okay, so that's kind of how we did this. Now I want to kind of like close up a little bit with part 3. What else can we do with all this stuff? So there's actually there's a very rich set of connections between the stuff I just showed you and a whole bunch of other areas of optimization and whatever. So in particular, this kind of problem formulation where we have all these coupled optimization problems that we solve jointly. Does that look familiar to anybody? So this is exactly, it turns out, a Nash game, a Nash equilibrium from game theory, which is a very, very rich problem domain that we've dabbled in a bit too. It turns out I was doing this stuff for contact mechanics, and I talked to someone who was a game theory person, and then I realized, oh wait, all the solver tools we're building actually are solving Nash equilibrium problems. Actually, so what we solve here is what's called a generalized Nash equilibrium problem. It's when you have a bunch of players and they all have constraints and they're trying to sort of do the best they can. So that kind of weird stacked set of KKT conditions we write down is actually the conditions for a generalized Nash equilibrium. So you can do other cool things with that. We've played around with autonomous driving for this, which is you have a bunch of drivers and they're trying to negotiate merging on the highway, for example. Has anyone heard of the frozen robot problem? It's a classic where if you have cars, if you have an autonomous car with collision avoidance constraints in its sort of setup where it's not allowed to hit anybody, if it's trying to merge into dense traffic, bumper to bumper traffic on the highway, it'll just sit at the bottom of the on-ramp and just freeze and not go anywhere. And the reason this happens is it looks over there and it says there's not a space in between the cars big enough for me to fit through. What do we do in that case? We're like, oh, well, if I just kind of nudge my way in there, I'm going to force the other drivers to make space for me, right? But if you just have collision avoidance constraints, you can't reason about that. That's fundamentally sort of a multi-agent game theoretic concept, right? What you're doing there is thinking about the other agent's behavior and kind of what they're going to do in response to you, right? And that actually is very naturally modeled by this Nash equilibrium thing. So we've done that kind of stuff. It turns out also under the framework we've kind of set up here falls a lot of classic robust control stuff. So minimax games, Stackelberg equilibria, all that kind of stuff also falls into here. And we've done like toy examples of that stuff where you're sort of games against nature where you have a disturbance input and you're trying to make that's trying to make your life bad and worse, and then you're trying to do the best you can in spite of this worst case disturbance stuff. So these are like toy examples of a rocket landing with fluid slosh modeled that way. They're kind of fun. So lots of interesting stuff there with like game theory kind of stuff with these ideas. We've also dabbled a little bit in manipulation stuff, and we're still working on that. This is kind of a fun example where we took that collision checking method that we have, decal, and it turns out if you do something like this, so I've always thought, a lot of the work in robotics decomposes objects into meshes or a bunch of like convex, it does like a convex decomposition where it breaks it into a bunch of convex bodies or whatever. And to me, this is always a little bit weird in that, the environment, if I'm going into a new space, I don't know what that stuff looks like a priori. But the robot, I know what the robot looks like a priori. So what we've done here is done this convex decomposition thing offline for the robot. But then the new object in the environment, we're modeling with a point cloud, which is kind of what you get already out of your perception system, right? So the idea here is this decall thing parallelizes across all those points super trivially. So we implemented it on a GPU with JAX, and it turns out we can do like 5,000 points in the same amount of time as one by putting it on a GPU. So now we can have like 5,000 points on this bunny, which has got a really weird, crazy non-convex geometry, and we can do it in real time because we can solve for all the points in parallel, which is kind of cool. And kind of, I think the idea here is to try to get ourselves closer to using the sensory data that we are getting on these things online in our simulations, right? So being able to pull this kind of really complex geometry natively, just take that point cloud with minimal processing and pull it right into your simulator. And then kind of along these lines, right, one of the things that I started hearing people talk about a bit more, we hear all this kind of stuff about the sim to real gap in robotics, especially RL kind of stuff. Sim to real transfer and how errors in the simulator make this harder. And it's always bothered me we haven't seen so much real to sim, what classically we would have called system ID in robotics with these simulators, where we kind of go do this stuff on hardware, and then rather than doing like transfer learning, where you're trying to take your offline learn policy and tweak it a little bit, why don't we take that same data and pump it back into the simulator and try to improve our models in the simulator so we don't have to do that again next time, right? So you can imagine all kinds of stuff like actuator models, compliance in the robot, weird friction effects, maybe better geometry, right? All this stuff we could be taking this rich data and pulling it back in and making our simulator, making our models better. And particularly the differentiability of this whole pipeline enables this, right? I can just do normal least squares kind of stuff on the data because I can diff through the whole simulator pipeline. Okay, and then last thing to tease briefly is this kind of idea, this like data-driven kind of sysid control stuff. We've actually started doing this recently with a few collaborators in quantum computing. It turns out that making qubits work, it turns out is hard and the models are bad, right? And there's lots of noise. So we started doing this sort of thing on these qubit systems with some collaborators. This is a quantum computer that one of our collaborators, Dave Schuster, who's at Stanford now, has, that we've actually run these kind of algorithms on and sort of improved the gate fidelities on these systems by quite a lot. And I think we're hitting kind of state-of-the-art fidelities now on these quantum gates. Kind of cool. Okay, with that, I have been extremely lucky to have all of these really awesome students work with me over the last 5 years or so who've really done all the stuff I just showed you. And that's who makes all the magic happen. So thanks to all these guys. And yeah, this is how you can find me if you want to harass me some more. And I'm happy to chat more, whatever you guys want to do right now.